Okay, let's unpack this. Welcome to the deep dive. Today, we're exploring the often unseen but utterly fascinating world of I/O systems. I/O simply stands for input-output, right?
That's it.
And it's the unsung hero that lets your computer talk to absolutely everything else. I mean, from your mouse click to loading a web page to saving a document.
Exactly. Anything going in or out.
Our mission for this deep dive is to sort of pull back the curtain on this critical part of computing. We're drawing our insights from Operating System Concepts 10th edition by Silberschatz, Galvin, and Gagne. Great book.
A classic.
Our goal is to demystify how your operating system manages all those incredibly diverse devices, transforming what feels like magic into something understandable. We'll explore the hardware connections, the software interfaces, the performance challenges, all while keeping it grounded in real-world examples you encounter every day.
And what's fascinating here is that I/O is so much more than just data in, data out. It really is. It's where the abstract world of your applications meets the physical reality of hardware. Understanding I/O means understanding the very foundation of how a computer operates, how it juggles countless tasks simultaneously without, missing a beat.
Right.
This journey brings together many foundational pieces, revealing the ingenious solutions that make modern computing possible, from the phone in your pocket to the massive data centers powering the internet.
So let's start at the most basic level then. How does a simple keyboard press, or save a huge file to a hard disk, actually communicate with your computer's brain, the CPU?
Yeah, how does that talk happen? It all comes down to a few core concepts.
First, you have ports. Think of a port as a dedicated connection point, like a specialized plug on your computer.
Exactly, a specific endpoint.
Then there's the bus, which is more like a common superhighway of wires, with a strict set of rules for data traffic.
A shared pathway, yeah.
A great example is the PCIe bus inside your PC.
Hmm.
It's a high-speed lane connecting your processor to quick devices like your graphics card.
Super common, super fast.
Devices can even be daisy-chained on a bus, where one device plugs into another and that one into the computer, like a string of holiday lights.
Kind of like that, yeah. One connects to the next in line. And managing all this communication is the controller.
Ah, the controller.
A controller is essentially a tiny piece of electronics, or sometimes a whole board, that operates a specific port, bus, or device.
So it's the middleman.
Pretty much.
Yeah.
For a simple device like a serial port, it might just be a small chip. But for something more complex, like, say, a high-speed storage network, the controller could be an entire circuit board with its own dedicated processor and memory. An HBA, they sometimes call it.
HBA.
Host bus adapter. Fancy term for a controller card. Even the hard drive sitting in your computer has a built-in controller handling sophisticated tasks like error correction and caching data.
Right. Okay, so with all these controllers, how does the main CPU actually talk to them?
Good question. There are two main ways.
Okay.
One is using special I/O instructions, which are specific commands built into the CPU that target a particular port address.
Like telling it, talk to port number 5.
Sort of, yeah. The other, and honestly the more common method these days, is memory-mapped I/O.
Memory map.
Yeah. Okay, what's that? This is where the controller's internal registers, think of them as little memory locations the CPU can read from or write to, are mapped directly into the CPU's regular memory address space.
So the CPU thinks it's just talking to RAM.
Exactly. It can use standard memory access commands, which makes interaction much faster, especially for things like, updating your screen's display memory constantly.
Gotcha. That seems way more efficient.
It generally is. Typically, a device controller will have a few key registers the CPU interacts with. A status register tells the CPU if the device is busy, if there's an error, or if it's ready for new commands.
Like a little status light.
Kind of, yeah. Then a control register is where the CPU sends commands, like start transfer or change mode. And then you have data in and data out registers for actually sending and receiving the information, the actual data bytes. Sometimes these controllers have small, temporary storage areas, like FIFO chips first in, first out, buffers like a little waiting room for data to handle bursts of information until the CPU or the device is ready.
Right, buffering the bursts.
Okay.
So imagine the CPU and the controller in a constant back and forth kind of handshake to move data. One very straightforward way is called polling.
Ah, polling. The simple way.
This is like the CPU repeatedly asking, are you busy? Are you busy? Are you done yet? Until the device finally says, no, I'm ready. Or yes, I'm done.
Constantly checking.
For example, if the CPU wants to send a byte to an output device, it has to keep checking if the device is free, then tell it to write, put the data in the right place, signal it's ready. The controller takes over, does its work, and then clears its status so the CPU, when it checks again, knows it can send the next byte. This loop happens for every single byte.
Busy work for the CPU.
Now, polling can work efficiently if the device is lightning fast and rarely makes the CPU wait. But if the device is slow, the CPU ends up stuck in a busy wait loop, just wasting valuable processing power that could be doing other tasks.
Exactly. Spinning its wheels.
This is where interrupts come in, a far more elegant notification system, right?
Much more elegant. Instead of the CPU constantly asking, the device basically raises its hand and tells the CPU when it needs attention.
How does that work physically?
Well, the CPU has a special wire, the interrupt request line. After executing pretty much every instruction, it takes a quick peek at this line.
Just a quick check.
A very quick check. If a device controller sends a signal there, the CPU immediately pauses what it's doing, carefully saving its current progress, its state.
Okay.
And then it jumps to a dedicated piece of code called an interrupt handler routine.
Like a special function just for this device.
Or for this type of interrupt, yeah. This routine is like a specialized troubleshooter. It quickly figures out which device caused the interruption, handles the urgent task like grabbing the data that just arrived, and then tells the CPU it can go back to its original work exactly where it left off.
Wow.
And modern computers, even when they seem idle, can process thousands of these interrupts every single second. It's absolutely crucial for keeping everything responsive.
Thousands per second. That's incredible.
It really is, and it's quite sophisticated now. The CPU needs ways to manage different interrupt priorities. Some things are more urgent than others. It needs to quickly find the right handler for each device, maybe using an interrupt vector.
A vector. Like a lookup table.
Exactly, a table pointing to the right handler code. And it needs to be able to ignore certain interrupts temporarily, mask them during really critical operations.
Makes sense.
And the kernel uses interrupts for all sorts of things beyond just hardware devices, like handling page faults when memory needs to be loaded from disk for virtual memory.
Right.
Or processing system calls. Those are essentially software interrupts that applications use to ask the kernel to do something privileged for them.
So interrupts are fundamental to how the OS operates, not just for hardware I/O.
Absolutely fundamental.
Okay, so interrupts are great for signaling when something's ready. What about moving large amounts of data? Imagine a disk drive needing to transfer a massive video file.
Right.
If the main CPU had to manage every single byte of that transfer, even with interrupts, it would be totally overwhelmed, wouldn't it?
It would be a huge bottleneck. That's where direct memory access, or DMA, becomes a real game changer.
DMA. Okay, what's the magic here?
DMA essentially offloads this heavy lifting to a special coprocessor, a dedicated chip called a DMA controller.
A separate little brain just for data transfer.
Pretty much. The main CPU simply tells the DMA controller, okay, here's the chunk of data on the disk, here's where it needs to go in main memory, and here's how many bytes to move.
Sets up the job.
Exactly. Once that command block is set up, the CPU is completely free to go off and do other work. The DMA controller takes over the whole transfer.
So the CPU doesn't touch the data byte by byte.
Not at all. The DMA controller talks directly to the device controller and directly accesses the main memory bus, moving data between the device and RAM without bothering the main CPU for each byte.
Wow.
It's like telling your assistant, here's the file, put it in that folder, and just let me know when you're done. Don't interrupt me for every page.
Ah, nice analogy.
Once the entire transfer is complete, the DMA controller sends a single interrupt back to the main CPU, just saying, hey, the job's finished.
Okay, so just one interrupt for the whole massive transfer.
Right. This dramatically improves overall system performance, freeing up the main CPU for computation, running other applications, whatever needs doing.
That sounds essential for modern systems. And crucially, all these I/O operations, whether it's simple polling or complex DMA, they have to be protected, right?
Oh, absolutely critical. Your regular applications running in user mode cannot be allowed to directly issue commands to hardware devices or scribble all over device controller memory.
Why not?
Well, imagine a rogue application telling the disk controller to just start erasing everything, or two applications trying to use the same printer at the same time.
Cool.
It would be chaos. A recipe for system crashes and massive security nightmares.
Right, total disaster.
So instead, user programs have to make system calls to the operating system. The request goes to the kernel.
Which runs in a special protected mode.
Exactly, privileged mode or kernel mode. The OS kernel then validates the request. Is this program allowed to access this device? Are the parameters reasonable? And then it performs the I/O on the application's behalf, ensuring security and stability for the whole system.
Got it. Protection is key.
Yeah.
So just to recap the hardware side,
Right.
we've got the specific connection ports, the shared data buses, the device controllers acting as middlemen, and they handshake with the CPU using either that repetitive polling or the much more efficient interrupt system. Plus the amazing power of DMA for offloading those big data moves.
Yep. That covers the core hardware interactions.
But wow, there's such a dizzying array of devices out there. Keyboards, mice, disks, network cards, GPUs, printers. How on earth does the operating system provide a uniform interface so applications don't need to know the specific details of every single one? That's our next big question.
And that is where the operating system truly shines, through the power of abstraction and software layering.
Abstraction, hiding the details.
Precisely. The OS cleverly hides the nitty-gritty differences between all those diverse I/O devices by presenting them to applications as just a few general standardized types.
Okay, how?
The real magic happens in the device drivers. These are specialized software modules, usually running within the kernel itself.
Right, drivers.
I've installed those. We all have. Each driver is custom written for a specific piece of hardware, or maybe a family of hardware. But critically, they all conform to one of these standard interfaces that the rest of the kernel expects.
Ah, so the driver knows the device specifics, but talks to the OS in a standard way.
You got it. This ingenious design means that when a new device is invented, the hardware manufacturers just need to write a driver for it that plugs into the OS's existing structure. They don't have to rewrite the whole operating system, and applications don't need to be rewritten either.
That's incredibly flexible.
It really is. And think about how diverse these devices are. Some, like keyboards, handle data as a continuous character stream, right? Byte by byte. Others, like hard drives, deal with data in fixed-size chunks called blocks.
Blocks, yeah. Like 512 bytes or 4 kilobytes.
Exactly. Some access data sequentially, like reading a tape. Others, like a disk, allow random access jumping anywhere.
Big difference.
Huge. Some are super fast gigabytes per second. Some are incredibly slow, a few bytes per second. And some, like maybe a special scientific instrument, can only be used by one program at a time, dedicated, while a hard drive can be shared by many shareable.
Wow, okay. That's a lot of variation.
It is. So the OS intelligently groups these into conventional types, making them much easier for applications to handle through standard interfaces.
And based on those types, applications have standard ways to talk to them.
That's the idea. For block devices like hard drives or SSDs, applications typically expect commands like read, write, and seek. Read a block, write a block, move to a specific block number.
Standard disk operations.
Yep. For character stream devices like your keyboard or a mouse or maybe an old-style modem, it's usually about getting the next byte or putting out the next byte. Very simple stream-oriented operations.
Makes sense. What else?
Then there's memory-mapped file access. This is a really cool and powerful technique.
You mentioned memory mapping for controllers earlier. This is for files.
Yeah, similar concept, but applied to files on disk. It lets an application treat a file, or part of a file, as if it were just a block of regular memory, an array in its address space.
So you just read and write to memory locations, and the OS handles the disk stuff automatically.
Pretty much. The system efficiently loads only the parts of the file you actually access, using the virtual memory system's demand paging. It's incredibly convenient for programmers, no explicit read-write calls needed, and often very fast, especially for large files or random access patterns. And then, of course, there are network devices. These are fundamentally different from local storage like disks.
Right, talking to the outside world.
Exactly. So most operating systems provide a distinct interface for networking. The network socket interface is a very common standard across Unix, Linux, Windows, Mac OS, pretty much everywhere.
Sockets, I've heard that term.
Think of a wall socket for electricity. It's a standard interface. You plug in any appliance, a lamp, a toaster, whatever, and it just works.
Okay.
Similarly, network socket commands allow an application to create a connection endpoint, the socket, maybe connect to a remote server or listen for incoming connections, and then send and receive data over that established network link. It provides a clean, unified way to handle all sorts of network communication.
Okay, so block, character, memory mapped files, and sockets cover a lot. What about controlling how the I/O happens? Like, does my program have to wait?
Ah, yes, the blocking versus non-blocking question. This is crucial.
Blocking means waiting.
Right. Most commonly, an application makes a blocking system call. For example, you call read. Your program just stops, it's suspended by the OS, and it waits. Waits until the data arrives from the disk or network. Only then does the OS wake your program up and let it continue.
Sounds simple to program.
It is the simplest model, yes, but imagine a web server. If it logged every time it waited for data from one client, it couldn't handle any other clients. Or think about your graphical user interface. If clicking a button caused the whole UI to freeze while waiting for a slow network download, that would be terrible.
Yeah, unresponsive apps are the worst.
Exactly. So operating systems also offer non-blocking I/O. With a non-blocking call, the OS returns immediately. It might return whatever data is currently available, maybe none, maybe just part of what you asked for. Your program can then check how much it got and decide what to do next. Maybe try again later, maybe do some other work.
Okay, so it doesn't freeze.
Right. And even more advanced is asynchronous I/O. Here, you initiate an I/O operation like start reading this file, and the system call returns immediately, just like non-blocking. But instead of you having to constantly check if it's done, the OS promises to notify you later when the operation completes, maybe by setting a variable, sending a signal, or calling a function you provided. A callback.
Ah, so the OS tells you when it's ready.
Exactly. This lets your program continue doing totally unrelated work while the I/O happens entirely in the background. It's very powerful for highly concurrent applications like servers or anything with a complex UI.
Makes sense why you'd need those options.
And one more efficiency trick. Some systems offer vectored I/O, sometimes called scatter-gather I/O.
Scatter gather. Sounds interesting.
It allows a single system call, like readev or writev in UNIX, to transfer data to or from multiple, potentially non-contiguous memory buffers all at once.
Instead of one read call per buffer.
Right. Imagine you need to read data into a header, then a main data block, then a footer, all stored separately in memory. Instead of 3 separate read calls, each involving overhead, you can make one readev call specifying all 3 buffers. The kernel handles gathering the data efficiently.
Less overhead, fewer system calls.
Exactly. It reduces context switches, system call overhead, and sometimes even provides atomicity for the whole transfer. Very useful in high-performance scenarios.
Okay. And you mentioned applications talking to drivers.
Mm-hmm.
Is there a way to send really specific, non-standard commands?
Yes. There's often a kind of backdoor mechanism for that. In UNIX-like systems, it's typically the IOTL system call stands for I/O control. It's essentially a generic way for an application to send arbitrary control messages directly down to a specific device driver, things that don't fit the standard read-write-seek model. Maybe setting a special hardware mode, getting device-specific status information, things like that. It provides flexibility without needing to constantly add new dedicated system calls for every weird device feature.
A flexible escape hatch, then.
Pretty much.
All right. So we have the hardware, the driver's abstracting it, standard interfaces like block-car sockets, non-blocking options. Now, here's where it gets really interesting, I think. The kernel I/O subsystem itself.
Yes, the kernel isn't just passing messages along, it's actively managing things.
It provides a whole suite of sophisticated services to manage I/O, doesn't it?
Absolutely, a whole layer of intelligence.
One crucial service you hear about is I/O scheduling. What's that about?
Well, think about a traditional spinning hard disk with a moving read-write head. If multiple applications all ask for data from different parts of the disk, the order they ask in might not be the most efficient. You could have the head jumping wildly back and forth across the platters.
Wasting time moving the arm.
Exactly. So the kernel's I/O scheduler can look at the queue of pending disk requests and reorder them to minimize that physical movement. Maybe serve all the requests near the beginning of the disk, then sweep across to the middle, then to the end. It's like a smart elevator algorithm minimizing travel time.
Optimizing the physical movement. That makes sense.
It can significantly improve overall disk throughput and reduce average response time for everyone using the disk. The kernel maintains wait queues for each device and keeps track of request status.
Smart. What other services does the kernel provide?
Another absolutely core service is buffering. We touched on buffers in controllers, but the kernel uses them extensively too.
Right. Temporary storage. Why does the kernel need them?
For several key reasons. First, like we mentioned before, to handle speed mismatches between devices or between a device and an application. Imagine reading data slowly from a network and writing it quickly to an SSD. The kernel buffer accumulates the slow network data and then writes it out in efficient bursts to the fast SSD.
Decoupling the speeds.
Exactly. Sometimes using double buffering, one buffer is being filled by the slow device while the other full buffer is being emptied by the fast one, then they swap roles. Very common technique.
Okay, Reason two.
Second, buffers help adapt to different data transfer sizes. Network protocols, for instance, often break large messages into smaller packets for transmission. The kernel uses buffers to reassemble these packets back into the original message, or vice versa.
Fragmentation and reassembly.
Right. And third, buffers are crucial for supporting copy semantics, especially for write operations.
Copy semantics, what does that mean?
It means that when your application calls write and gives the kernel some data from its memory, the kernel usually copies that data into its own internal buffer before the write call returns control back to your application.
Why copy it? Why not just use the application's memory directly?
Because once the write call returns, your application might immediately change the data in its own memory buffer. If the kernel was still writing the original data from your buffer to the slow disk in the background, you'd get corrupted data. By copying it first to a kernel buffer, the kernel guarantees that the data written to the device is exactly what the application provided at the moment it called write, regardless of what the application does afterward.
Data consistency. Got it. That's important.
Very important. Closely related to buffering is caching.
Buffers and caches. They sound similar.
They often use the same memory, but the concept is slightly different. A buffer is primarily about holding data temporarily during a transfer. A cache, on the other hand, is a region of fast memory, like RAM, that holds copies of data that also exist elsewhere, usually in slower storage, like a disk.
A copy for faster access later.
Exactly. The kernel often uses its buffer memory also as a cache. For example, when you read data from a file, the kernel might keep that data in a buffer cache in RAM. If you or another application ask for the same data again soon, the kernel can just provide the copy from the fast cache instead of having to go all the way back to the slow disk.
So it avoids or defers the physical I/O. Huge performance win.
Huge. Disk caching is one of the most important performance optimizations in any OS.
Okay, what about managing devices that can't be easily shared, like printers?
Right. For devices like printers, where output from different applications would get jumbled together if they wrote directly, the OS uses a technique called spooling. Comes from simultaneous peripheral operations online.
Spooling, like the print queue.
Exactly. When applications print, the OS doesn't send the output directly to the printer. Instead, it intercepts it and writes it to a temporary spool file on the disk, one file per print job. A separate system process, the printer daemon or spooler, then reads these files one at a time and sends them to the actual printer hardware in an orderly fashion.
Prevents the output from getting mixed up.
Precisely. And for devices that truly cannot be shared at all, like maybe an old magnetic tape drive that needs exclusive access for a backup, the OS usually provides mechanisms for a process to request exclusive device access, locking it so no other process can interfere until it's released.
Okay. Coordination for shared and unshared devices. Makes sense.
And inevitably, things go wrong, hardware fails, networks get congested, so the kernel has to manage error handling.
What can it do?
Well, it can often recover from transient failures. Maybe a network packet got dropped, the kernel can just retransmit it. Maybe a disk sector had a temporary read error. The kernel might retry the read a few times.
Automatic retries. Nice.
But for permanent failures, like a physically damaged hard drive sector or a dead network card, the kernel usually can't fix it. In that case, it typically has to report the error back up to the application, often through an error code like errno and UNIX, letting the application decide how to handle the failure. Good device controllers often provide very detailed error information to help diagnose the problem.
So resilience where possible, reporting when not.
That's the goal.
And all this relies on the kernel keeping track of everything, right? Open files, device states.
Absolutely. The kernel maintains numerous complex internal data structures to manage all this state. For example, when you open a file or a device, the kernel creates an entry in a system-wide open file table.
A big table tracking everything open.
Yeah. And UNIX-like systems, in particular, use a really elegant, flexible, almost object-oriented approach here. Each entry in the open file table doesn't just store info. It also contains pointers to the specific functions, the methods, if you like, needed to operate on that particular type of file, whether it's a regular user file on disk, a raw block device, a character device like the console, or even a network socket.
So the same read system call can work differently depending on what kind of file it is.
Exactly. The generic system call code looks up the right function pointer in the file's table entry and calls that specific implementation. It's very modular and extensible.
Very cool. One last kernel service, power management. That seems huge now, especially on mobile.
Absolutely critical. Operating systems play a massive role here. In big data centers, the OS might use strategies to consolidate workloads onto fewer machines and then power down idle servers entirely, or power down individual components like CPU cores or network interfaces when they're not needed, saving potentially megawatts of electricity and reducing cooling costs.
Wow. And on my phone.
On mobile devices like Android or iOS, it's even more aggressive. The OS constantly tries to put the device into a very deep sleep state, sometimes called power collapse, where almost everything is shut down except for the bare minimum needed to wake up quickly.
To save battery.
Exactly. It involves detailed component-level power management, where the OS and drivers track the usage of every little piece of hardware, the Wi-Fi chip, the GPS, the screen, and power them down individually whenever possible. Applications can also use things like wake locks to tell the OS, hey, I'm doing something important like downloading an update. Please don't go into deep sleep right now.
A constant balancing act between responsiveness and battery life.
A very complex one, yes. Standards like ACPI help manage the hardware side of this.
That's an incredible list of services from the kernel's I/O subsystem.
Yeah.
It's doing I/O scheduling, buffering, caching, spooling, device reservation, error handling, power management, maintaining all those data structures, all while providing secure access. It's truly the maestro conducting a very complex symphony.
It really is orchestrating a huge amount behind the scenes.
So after all that, let's connect the dots. What does this all mean when I, the user, just double-click a file icon or typecat myfile.txt? How does my application simply asking for a file name actually get translated into low-level commands for a specific disk controller buried deep inside the machine?
Right, tracing that request is a great way to see how it all fits together. It's a fascinating journey of translation.
How does it start? Finding the device.
Yeah, first the name needs to be resolved to a specific device. In older systems like MS-DOS, the device name was often part of the file name itself, like C myfile.txt.
Right, the drive letter.
But UNIX-like systems took a more integrated approach. They incorporate device names seamlessly into the regular file system namespace through the concept of mounting.
Mounting a file system.
Exactly. When you access a path name like homeuser myfile.txt, the kernel consults its mount table. This table maps directories, mount points, to specific storage devices. So it figures out that home user is on, say, device number 8.1.
A major and minor number.
Yep. The major number, like 8, typically identifies the device driver responsible for this type of hardware, maybe the driver for standard iDesita disks. The minor number, like 1, then selects the specific instance of that hardware, maybe the first partition on the first disk handled by that driver.
So major driver type, minor specific device.
You got it. Once the kernel has that major-minor pair, the major number tells it which driver code to call, and the minor number tells the driver which physical device and controller port or memory mapped address to actually talk to.
That seems really flexible.
It's incredibly flexible.
Yeah.
This multi-layered lookup path, name to mount point to device numbers, major number to driver, allows you to easily add new storage devices, use different types of file systems, and load new device drivers without recompiling the entire operating system kernel.
And you mentioned dynamic loading of drivers.
Yeah, most modern OS don't even need all the drivers built in anymore. They can detect when you plug in a new USB drive, for example, identify it, find the correct driver module on disk, load it into the kernel memory on the fly, and then mount its file system. When you unplug it, the driver can often be unloaded too.
Very dynamic. Okay, let's trace a simple read, call, step by step, to see all these layers in action. Say, my program wants to read data.
All right, the life cycle of a blocking read request. Here we go.
Step 1.
Step 1. Your application process issues the read system call, asking for data from an open file.
Okay, makes the call.
Step 2. The request traps into the kernel. The kernel system call handler first checks the parameters. Is the file descriptor valid? Is the memory buffer okay? Then, crucially, it checks the buffer cache. Is the requested data already in RAM?
Maybe it was read recently?
Exactly. If it's in the cache, a cache hit. The kernel just copies the data from the cache to the application's buffer. The system call returns almost immediately, and the process continues. Done. No physical I/O needed.
Nice and fast. But if it's not in the cache...
Step 3. If it's a cache miss, then a physical I/O operation is required. Since this is a blocking read, the kernel puts the application process to sleep, moves it to a wait queue for this I/O event. The I/O request is then scheduled, potentially reordered by the I/O scheduler, and eventually passed down to the appropriate device driver found via the file's major minor numbers.
Okay, process leaps, request goes to the driver.
Step 4. The device driver takes the request. It might need to allocate kernel buffers, translate the file block number into a physical disk address, and then it constructs the actual low-level commands for the hardware device controller and sends them out. For example, writing to the controller's command registers.
Driver talks to the controller.
Step 5. The device controller receives the commands and tells the physical device, for example, the disk drive, to perform the operation, move the head, spin the platter, read the data.
Hardware does its thing. Slow part.
Often the slowest part, yeah. Let's assume DMA is used for the data transfer. Step 6. The device controller reads the data and works with the DMA controller to transfer that data directly into the kernel buffer that the driver allocated earlier. Once the entire transfer is complete, the DMA controller generates an interrupt signal to the CPU.
Interrupt, we're done.
Step 7. The CPU detects the interrupt, saves its current state, and jumps to the interrupt handle routine for the DMA controller or the device. This handler processes the interrupt, figures out which request just completed, and signals the device driver, often by waking up a part of the driver that was waiting. Then the interrupt handler returns.
The interrupt handled, driver notified.
Step 8. The device driver code, now knowing the I/O is done, performs any necessary cleanup, and then signals the main kernel I/O subsystem that the original read request has been fulfilled.
Driver tells the kernel.
Step 9. The kernel I/O subsystem now takes the data from the kernel buffer, where DMA put it, and copies it into the application's original memory buffer. It also prepares any return codes, like the number of bytes read. Then, crucially, it moves the application process from the wait queue back to the ready queue, making it eligible to run again.
Process is ready to wake up.
Step 10. Eventually, the OS scheduler picks the application process to run again. It resumes execution right after the read system call, finds the data in its buffer, gets the return code, and continues on its merry way.
Wow, that is a lot of steps.
It is. That seemingly simple read command involves numerous handoffs between the application, kernel subsystems, drivers, controllers, DMA, and the physical hardware, plus context switches, interrupts, data copies, scheduling decisions. It's a testament to how much complex orchestration is happening constantly under the hood, even for basic operations.
Absolutely. And all that complexity must have a huge impact on overall system performance, right?
Oh, massively. I/O is very often the bottleneck in system performance.
How does it impact things?
Well, think about it. All that driver code executing, the kernel scheduling decisions, handling interrupts that all consume CPU cycles, every time the system switches context between user mode and kernel mode or between different processes, there's overhead, and it often flushes the CPU's own internal caches, slowing things down further. The interrupt handling itself, while efficient compared to polling, still has a cost. Saving state, running the handler, restoring state, it takes time. Thousands per second adds up.
Right.
And moving data around often involves multiple copies in memory, maybe from the device controller to a kernel buffer, then from the kernel buffer to the application's buffer. Each copy consumes memory bandwidth and CPU time.
So CPU load, context switches, interrupt costs, memory copies, it all adds up.
It really does. Network traffic can be particularly demanding. We mentioned typing one character in a remote session. The sheer number of interrupts, context switches, data copies, protocol processing layers like TCP/IP involved on both the local and remote machines just to echo that one character back is staggering if you analyze it closely. It essentially doubles the work.
That's wild. So how do system designers try to improve I/O performance?
There are several key principles they focus on.
Okay, what are they?
1. Reduce the number of context switches. Fewer switches means less overhead.
Makes sense.
2. Reduce the number of data copies in memory between the device and the application. Maybe use techniques like DMA directly into user buffers, if safe, or clever buffer sharing.
Avoid redundant copying.
3. Reduce the frequency of interrupts. Use larger data transfers per interrupt, like with DMA, have smarter controllers that can bundle notifications, or even use polling intelligently in situations where you know the device will be ready very quickly.
Fewer interruptions.
4. Increase concurrency by using components that can operate in parallel with the main CPU, like DMA controllers, or even dedicated I/O processors or channels like you see on mainframes. Offload the work.
Let hardware do more.
5. Following from that, move processing primitives into the hardware itself. If a common task can be done efficiently by the device controller, like calculating a checksum, let it do it instead of the main CPU.
Smart.
And finally, 6. Balance the performance of the different system components. the CPU speed, the memory speed and bandwidth, the bus speed, and the I/O device speeds. If you have a super fast CPU but incredibly slow I/O, the CPU will just sit idle waiting. You need to balance the whole system.
A holistic view. Those make a lot of sense.
And it's interesting to see how I/O functionality often evolves over time.
How so?
Well, typically a new I/O algorithm or feature might first be implemented purely at the application level, maybe using libraries or frameworks like Fuse, file system and user space. This is flexible, easier to develop, and bugs are less likely to crash the whole system.
Safer to experiment in user space.
Right. Then, if the feature proves really useful and performance becomes critical, it might get re-implemented down inside the kernel. This usually offers much better performance because it avoids context switches and can directly access kernel structures. But it's much harder to develop, harder to debug, and a bug can crash the entire OS.
Higher risk, higher reward.
Exactly. And finally, for the absolute highest performance, the core functionality might eventually be moved directly into the hardware, into the device controller, or specialized I/O chips. This offers the best speed and parallelism, but it's the most difficult and expensive to design and change, and the least flexible.
Application, then kernel, then hardware. A common path.
A very common progression for performance-critical I/O features, yeah. And we're constantly seeing this interplay as device speeds increase, especially with things like modern non-volatile memory NVM devices like super-fast SSDs. They put immense pressure on the OS and software layers to keep up.
The software has to evolve to match the hardware speed.
Constantly. It's an ongoing challenge.
Wow. We've covered a tremendous amount of ground today, really diving deep into this intricate world of I/O systems. We started with the basic hardware connections like ports and buses, the controllers, and how they talk using polling or interrupts, plus those crucial DMA controllers.
The physical layer.
Then we looked at how the operating system provides that vital, uniform interface using device drivers and standard access methods like block, character, memory mapped, and sockets.
The abstraction layer.
We explored how the kernel actively manages I/O with scheduling, buffering, caching, spooling, error handling, and even power management.
The kernel's crucial services.
And we traced how a simple request travels through all those layers, from your application right down to the hardware and back, highlighting the performance implications of that complexity.
Yeah, putting it all together. This really raises an important question, maybe something for you, the listener, to think about.
Oh.
Considering how much effort, how much complexity goes into making I/O efficient and seamless, all those tricks like reducing context switches, optimizing data paths, offloading tasks to specialized hardware, what do you think is the next frontier in I/O system design?
Good question.
Will future operating systems need to lean even more heavily on specialized hardware accelerators? Or will we see entirely new software paradigms emerge, maybe radically different ways of thinking about data movement to wring out every last bit of performance, especially as I/O devices themselves become unbelievably fast and incredibly diverse?
Will the software change fundamentally, or will the hardware take over even more?
It's a fundamental challenge, and it's one that continues to drive a huge amount of innovation in computer science and engineering. Where does I/O go from here?
That's a fascinating thought to end on. Well, thank you for joining us on this deep dive into I/O systems. We really hope it's given you a shortcut to being well-informed about this critical, complex, and often invisible part of your computer, and maybe sparked your curiosity to learn even more.